of our energy at the end of the day. So my name is Huamin Qian. I have been with Red Hat for over 7 years. I joined Red Hat as a great time, starting to work on the Kubernetes and OpenShift while this becomes the mainstream technologies back then. And moving over to a different cloud native upstream and downstream projects. I recently got this opportunity to lead the sustainability efforts as the emerging technologies as the office of the CTO. And during this time, I feel that the sustainability in terms of energy consumptions, optimizations, and carbon emission reduction, this is a great effort to do, both technology and environmentally wise. So I'd like to share with you some of our work and visions in this area. So first of all, I really want to share with you what Red Hat is doing in terms of sustainability. So good for me is we have been having a lot of conversations today about digital transformations, cloud computing, edge computing, and industrial 4.0. And this is all relevant to date because according to certain studies by World Bank, digital transformation is going to reduce greenhouse gas emission by 15%. That's quite significant and very lofty goals for what we can do and what we can do in this area. Improving technology efficiencies and push technologies everywhere in industrials and in digital technologies is a huge boost for energy sustainability. And Red Hat has a lot of products and technologies in these portfolios. So if you are paying attention to what we have had today, so in the talks today, cloud computing, edge computing, and Industry 4.0, you will get a sense that what we do is quite relevant to sustainability as well. Second of all, I want to touch base on these green technologies that Red Hat has been doing and is continuing improving. So we have technologies in these categories: resource optimization, power management and measurement, and overhead and waste reductions. So when you are using OpenShift on OpenStack, you will come up to the idea that has been a lot of been done for resource optimization. The traditional single server kind of computing forms is going to virtualize in virtual machines and containers. And resources are quite freed up. That will lead to a lot of technologies, the OpenStack, OpenShift. These become the mainstream technologies in cloud computing and resource optimization. That will significantly improve the utilization of hardware. So you will get the more benefits on power savings and eventually come to sustainability. When we come to the idea of how much power that has been used on my servers, on my workloads, and specifically how can I use this information for managing our workloads and managing our power budgets, Red Hat has been doing a lot in this space. So we are coming up with, we are going to dive in deeper in the next slides. We are coming up with technologies that help you, the end customers, the developers, and as well as the system administrators to get a benchmark, to get insights into the energy consumption by their workloads, and to take these insights into their operations and eventually building up technology stacks to optimize the energy consumption. Lastly, when you are coming to technologies, this may not be immediately straightforward to you, but if you are using technologies, for example, the serverless, right? So the serverless technologies can scale up and down automatically. That will reduce a lot of idle power that's not used for computation without your personal manual management. And this will significantly reduce the overhead of using the computation resources. And it will also come to the technology like a Quarkus, the Java runtime. Quarkus is able to improve the densities of applications significantly, reduce the startup overhead. That's the overhead we are talking about in terms of energy consumption and sustainability eventually as a goal. Very lastly, I will come to the Red Hat corporate commitments. So this I copied from the 2021 corporate report. So our chairman, CEO by then, Paul Cormier, he made such statements. As Red Hat, as corporate leadership, from the corporate leadership commitments, has been taking a lot of efforts and steps and actions into sustainability. We have our internal climate change community of practice. We have this regular course, how Red Hatters can contribute to environmental sustainability. And that will come as the action items into our corporate agenda. So, this is all about energy. So maybe you can just do some of our energetic exercise end of the day. So let's just say, if you have any of the agreements, you have some insights, have some ideas about what you do in your operation, organization, and in your daily job, maybe you can just shake hands and raise your hands as a signal that this is some actions from technology, from products, and from corporates. This is what you do and what your organization is doing. So that's going to be consistent with what our visions are and what our commitments are. Next, I'm going to talk about what we do in terms of innovations and visions and the Office of CTO in Red Hat. So if you sum up in a nice way, we call it real, right, just for convenience, and reporting, instrumentation, and optimization. So what we do here is as an end user, as a system admin, and as well as the, let's just say, the owner of products and IT products, you want to have a sense of how much energy consumed by your systems, by hardware, by software, and by workloads and day-to-day operations. If without this information, you do not know starting from where you will get this action started. If you were to say, I'm going to reduce the utility bill for my data center, you probably has a lot of struggles. Where should I get started? Should I reduce the number of servers? Should I reduce the number of users? Should I reduce the number of workloads? You want to target the highest inefficient workloads the highest one as possible. So you will have the right target. So this first project we call the Kepler. The project Kepler is towards that direction. It started as the motivation that we want our customers to have insights into the workloads, the energy consumption, and of their workloads, and using that as a cloud-native metrics that will be fed back to their dashboards and fed back to their reporting channels, and then they can build up the more efficient ways to identify their workload energy consumption. It's automated and as accurate as we can for that technology. Once we have these insights, and you may come up to the next stage of iteration, can I reduce the energy consumption? For that, we have two solutions, also cloud-native way. So when you're using OpenShift, you have this concept of scheduling, right? So you have your workloads, and you want the workloads to come to which of the compute nodes, that's with the run of workloads. As the time of scheduling, meaning that before the workloads is actually executed, we're trying to identify the best compute nodes for this type of workloads. This comes with two things. One is that we have to have the ideas about the capacity, the characteristics of the compute node, and then we have to come up with the ideas of what the workloads, the new workloads is going to do to add up to the existing workloads. That will generate additional power consumption profile. And we are using the most efficient estimated profile for your schedule, for your workload scheduling, such that the resultant runtime energy consumption is expected to be more efficient than without this technology. We call this project PICS. It really stands for Power Efficiency Aware Kubernetes Scheduler. It's a cloud native in Kubernetes, OpenShift native. And we hope that can be get a preview in a very early time frame. So for the last time, for optimize, so the idea is that once your workloads has been running for a while, and you identify that workloads has been consuming energy suboptimally, can this be tuned in a way that can be more energy efficient? So I will just using certain heuristics, something like a CPU frequency, because as this is probably one of the quotes I need to use for today. The applied science, the engineering is really application of science. Right? So according to science, the energy consumption has two determination factors. One is about voltage of the the circuits operating under. The other one is the frequency, as what frequency this circuit is operating at the moment. So if you are tuning down the frequency, just like the treadmill, you slow down on your treadmill, the less energy is going to consume, the less calories you are going to burn. The same idea we are going to use for optimize. If you identify you are slowing the workloads, it's going to slow down. Maybe for at the night of the time, so you are not using too much energy. So we are going to tune down the frequency such that your workload is continue to run without disruption, but the energy consumed is much less. So we call that optimization. It's going to be done in the cloud native way as well. We're using this cloud native things called vertical path scaler. That's where the project Kepler comes from. So it's really about scale the resource up and down for the running part without kill it, without disrupt it. The only thing you need to do is to lower the frequency as the best optimal time we identified by the controller. So as this presentation, I'm going to focus on the Kepler project first. If you have future opportunities, I would love to share with you more information about the PICs and Kepler. So let's come to the problem of what the cloud native power management is about. So of course, we want to have this measurements as accurate as possible. Okay? This is the same thing as your power meters at home. You do not want your meters to go wrong directions when you are using for example, your computers. So we want this to be accurate, and we want to be fair. Meaning, when we say fair, it means two things. One is that when you have the co-located workloads on the same server, we do not want to, certain noises introduced into the system such that your workload is negatively impacted by somebody else's workloads. So we want to have this isolated environment. We want to use the native instructions to predict the power consumption at different levels. So lastly, we want this to be done at a hierarchical level. So we want it down to be at the process level, as you can see in this picture, in the cloud native environment. We want this can be done at the container level, and more importantly, straight to the end customers at the pod level. And we as the different levels, you have different complexities. Things like the co-located context switch, and how quick as the time slots measured in the right place, and what are the heuristics we need to get from the shared platform on the operating system. So we just got the talk from Chris about these accelerators. I put a picture here that we focus on different components in the system, mostly about CPU and memory. It also works with the GPU as an accelerator, and we are also planning to add more support as long as we can know what's the correlation between our energy consumption with the operating system as well as from the device itself. So Kepler is really built into these ideas of cloud native, efficiency, and science, and to support the accuracy claim. So if you are thinking about Kepler, you just need to have 3 letters, 3 R's. Right? Reporting is the major goal. What it's going to report is the difference, makes a difference. We do not just want you to get the numbers. We want you to have visual and an intuitive dashboard. So the end users, cloud operators, as well as the people who from different the assets owners can just use the dashboard to have a vivid intuition of the energy consumption by workloads, by tenants, and by the time of the day. We support the cloud native dashboard called Prometheus and Grafana, but if you have other things to integrate, we are glad to hear from you. The second is that we do not want to use a lot of resources to get this reporting capability. because that's where defeats the purpose of being energy efficient. So we use our latest technology, it's called eBPF, and to get using very little system resource to get the information we need to build up these reporting capabilities. And lastly, we have regression models. The regression model is really based on the science that has been done for many years for power management, measurements for workloads. So the regression models we use is going to be a distinction between Earth and the other projects, which I'm going to cover next. So the Kepler project is really not the first one in this space. So the motivation of starting Kepler, we have to look back at what has been done in this space before. So many of you probably already know these three projects, the cloud carbon footprint, and if you are the end customer of AWS, Amazon, and Microsoft Azure at the same time, they offer this carbon footprint tool to tell you, give you a dashboard of what your cloud resources has consumed the carbon footprint, have produced carbon footprint. And there's yes, another open source project can give you similar capabilities of energy consumption at different levels. So I'm using this opportunity to discuss why Kepler is different from these projects and products. For certain projects in the categories of power estimates, for one of those is the cloud carbon footprint, is focused on the configuration of the hardware. And if you are using a certain instance of cloud Amazon or Microsoft Azure, you can get the estimates of how much carbon is being used by that instance. But it does not give you the idea about your workloads. If you are running the instance, for example, by multi-tenant environments on a single instance, you do not have straightforward answers how much consumed by each of the tenants. Similarly, if you have multiple services, for example, one is using database, the other one using web app, you do not have ideas about which app is using how much energy. And fundamentally, cloud carbon footprints is based on the methodology that's yet to be validated by science. So what I mean by science, that the numbers come up with cloud carbon footprints or any of these instance-based estimates has to be correlated with the physical measurements, the electrical. You have to attach the power meters to the electrical circuits and measure the power consumption to make sure the estimates and the measurements match. So the way we are doing the Kepler is built on top of this research and using the same regression models for power estimates. So I feel that we have been on a path that's been validated by scientific research. For AWS and Microsoft Azure, the dashboards give you a lot of ideas, but it's missing certain aspects. So if you want to get fine-grained information, for example, if you are using the instance to stand up your Kubernetes and OpenShift clusters, if you want to get more insights about, for example, if you are using multi-tenant environments, multi-application environments, how much energy you used by these tenants and by certain applications, you're still missing this information from this dashboard because it's based on service level, for example, the EC2 or EBS. So this is not the information you can use intuitively or straightforwardly into your dashboard or for your reporting. So this distinction of Kepler is that it can give you another layers of information and it really can build up to the level you want. For some other projects called Scaphandra, and yet another research projects in the open source space. Our methodology is different from them. Is that again, it comes to the science-based method, and that's what we are using for power estimate. The other one is that we are trying to support as many platforms as possible: bare metal, virtual machines, x86, ARM, or even other platforms. So we are trying to using the single tool that can be portable and the same interface, same deployments. You can use this everywhere. So I will just get this very quickly. So for Kepler, it's a layered technology. So we are collecting data from systems so that you can just use this metrics to build up the models for energy consumption. These models are based on scientific research that has been done over the decades. And we use these models and we continue to refine these models to give the upstream, the upper layers reporting tools to help them to export this information. So the metrics can be exported and you can use this metrics to build out the dashboards and build out your native reporting tools. And this is one examples of the dashboard you can use. This is based on Grafana and Prometheus. So on top of this dashboard, this is very customizable. On top of this dashboard, you can see three things. This equivalence to how much carbon, to how much energy used, generated by petrol and by natural gas, and by how much carbon emissions equivalents generated by coal, by oil, and by natural gas. And on the middle one, the zigzag one, this is the energy used by different components on certain containers and certain parts. This could be a CPU, this could be a GPU or DRAM. So I'll give you a breakdown of what components generates how much energy. And on bottom left, on bottom right, the green bar, that is about the worth of the part at the part level. What's each of the parts, the impacts of each of the parts in the namespace, what's the variations, and what's their relative strength in the carbon energy consumption. And you can also have different levels of reporting based on each of the namespace and build up on each of the over each of the time frames that you're observing. So again, the highlight of this dashboard is that we can report energy consumption at different levels, a container level and a part level, and with a namespace level. And you can customize this reporting according to different benchmarks, equivalent to how much carbon generated at the different places. We can extend this dashboard to different environments. For example, if you can integrate more information into the dashboard for the grid carbon intensity, right? So if you have know how much carbon used by your grid power, you can incorporate that information to have a vivid real-time information about carbon generated by the workloads by the utility information. So the Kepler project is really a collaboration between Red Hat, IBM, and Intel. We want to bring up these developments and impacts into a broader cloud-native user space community. We are looking for more opportunities to present this work and get more use cases. So if you happen to have what you need in your organization, have a use case you want to support, and have more importantly, if you want to contribute to the projects, we are more than happy to help you to get there. Right. This will come to the demo. Before the demo, I just want to quickly summarize what we are going to do in this demo. So today, we have been talking about microchips from the morning. So this demo also based on microchips. So it's a single node OpenShift deployment on a real hardware on IBM Cloud. It has 32 cores of the CPU and has a NVIDIA GPU. So we stand up the Kepler by applying the YAMLs. The YAML is developers UI, but if you are an end user, you are probably more familiar with the operator, which is under development at the moment. So once we deploy the Kepler, we create a lot of integrations. So we deploy Prometheus, we deploy Grafana, which is collecting this metrics and then display the dashboard. Once everything at the infrastructure level is ready, we generate some workloads. First, we generate a CPU-intensive workloads, and then we generate a GPU-intensive workloads, and we look at the dashboard activities on the Grafana dashboard and see what is going on at that moment. At the end of this workload demos, we are also looking at how much resources consumed by Kepler to give you some ideas of what's the resource consumption by Kepler. So again, this is going to be three phases. One is the deployment, the other one is the benchmark of different workloads. The very last one is just the demonstration of Kepler is really a less resource consuming application. Just stop me whenever you feel necessary, so we can just start from there. Right, so this is the Microchip Cluster we are using. Again, this is based on Microchip is a very rapidly progressing project. This is based on an early release. And if you are using latest Microchips, the UI could be different. And this is the YAMLs that we are using to deploy Kepler. Again, this is all in the project documentation page. And in the future, we are going to use an operator, so you are going to be more user-friendly. We look at this manifest. There's really about three things. One is the access control. The other one is the deployment. The third thing is about the service. The service is going to be used for the Prometheus to scrape the metrics from the Kepler endpoint. Once that is deployed, and you're going to see the Kepler part running. I'm just a second ahead of time. Okay, so once this Kepler deployment is ready, you can see the paths, the Kepler paths running. Okay, so now it's started. Again, this is because this is a single node, so you only see one Kepler path. It's a daemon set, so every node that's supposed to daemon set node, we are just supported. And the quick validation is through the log. Check the logs of the parts. If you see certain information, like how much energy is being measured by each of the parts, that's a very good sign. This Kepler is started running. Again, this is early versions of Kepler. In the future, we are going to use more automated health detection using health probe and Redis probe. This is more cloud native way. So now we validated Kepler is running. We're going to deploy this infrastructure like Prometheus and Grafana, and also install the service monitor endpoint. So that's Prometheus. We just know how to scrape the information from Kepler. And then once again, just going back to the technology. So Kepler is really a Prometheus matrix exporter. So there's an endpoint you can just directly go into and see if that's information is presented by that endpoint. This is just another validation. That's once you see this matrix, this means Kepler is running healthily in the system. Again, this is going to be built up into Kepler's capability as well. And we are happy to work with the community to improve the productization of this project. Okay, so now we are coming to the Prometheus. So we're going to, this is using completely upstream projects. So we're going using this Prometheus operator, and we are using the setup, using the instruction from the upstream project to install Prometheus from there. If that is too small for you, just let me know. If I can, see if I can have any magic to make it bigger. Okay, so once we set up the Prometheus, and then we install this Prometheus CRDs and infrastructure, we're coming back to Kepler, and getting Prometheus installed is about two phases. One is there's a setup phase and the CRD phase. Okay. Now, when the Prometheus is ready, we're going back to Kepler again, just to deploy the service monitor endpoint, service monitor definition. Again, this is a very developer-focused process. Once we have the operator, everything will be automated. It's just one click away from installing Kepler. This just gives you the intuition what is working behind the scene to make things work. So at this point, we are deploying this service monitor. The service monitor is the connection between the Prometheus and the Prometheus exporter endpoints. So the Prometheus will know how to scrape and what service to scrape and what's the endpoint it should go into to that service. Okay, So at this point, the service monitor is installed. We can see this Kepler. Let me pause it here. Oh, did I go in too fast? Okay. Oops. Sorry, it's an exercise for me. Hopefully, the more I practice, the more sustainable my presentation can be. All right. It's not too bad to watch it second time, because each time I watch these processes, I remember I have to keep in mind what the operator needs to do, not to break things down. Okay, so once the service monitor is ready, and we'll just check out the what's the install of a service monitor by. Okay, so you see here the Kepler exporter service monitor is installed here, and that's what we want to verify. Now we need to take back the UI. So the way, as a developer, we typically do, you just go into SSH tunneling. So we opened up the local ports and we SSH to that's a remote port. And then we bring the service to the remote ports. And then we can ask the local machine, in this case, a Mac machine, we can just look at what is going on the UI. So this is we are creating this SSH tunnel. Now, once the tunnel is done, we have to do the post forwarding from the Prometheus to the remote ports we created. That's will be tunneled to the local ports. Again, this is a little bit hacky. If you have your, for example, the OpenShift cluster, it can be done in a more cloud native way. You use this service endpoints that will directly created as the OpenShift routes, and you can use that routes to view your service. This is a little bit development-focused way to look at the metrics. All right, so this is the Prometheus dashboard. What you need to see here is that there's a certain metrics to validate, and you want to see the metrics is over there. The numbers over there are making sense. And then we validate everything is in good shape. And the next thing we're going to do is just make sure this metrics can be used in the Grafana dashboard. All right, this is the validation. Again, I just want to iterate that both Microchips and Kepler are rapidly progressing. So what you are seeing here may have changed in the future, but only for better way. Right. So the energy we are using here, we are just trying to see different paths, different namespace, and to see the progress of this reporting. Because Grafana, the Prometheus is really a time series database. So you see here is the time progressed over the numbers progressed over the time. Now we validate the Prometheus. Prometheus is going to be used by Grafana dashboard to show up the dashboard we just see in the picture. The same way we're going to use it to tunnel the Grafana UI to our local machine. It's going to create yet another SSH tunnel. And once we are on the Microchip's host, we are going to post forward the Grafana service to the remote ports we created and tunnel back to the local machine. So, all right, the first time you go into Grafana, you can create the username, and this is going to the basics. So you create the identity for your Grafana access. So here we just go into the Grafana dashboard, and from there you can import the dashboard you want to display. So we have pre-created a number of dashboards over there, and then we just import from our local host. So you can either upload your JSON, or you can just copy paste your JSON file over there. It's already downloaded, so we just upload from a local machine. Oh, yeah, everything's here. So we got some of the numbers showing, just as we displayed earlier. This is the information about the energy consumption by the different parts, as the namespace level, as the parts level. And we can also ranking up as different namespace. You can also rank between different tenants if you know their corresponding namespace. And if you have yet another layers to integrate, you can also integrate that with Grafana as well. Have more information over there. It's really a fun exercise to build out a dashboard. Okay, so now we have the infrastructure ready. We are going to run some of the quick workloads. As we are actually running out of time, so I just show the CPU workloads. The CPU workloads is really just cat, the random number generator to generate some of the CPU loads. And we see that's part, what's the progress of the energy consumption by that part. And I'm going to skip the GPU demo, just for time's sake. But in the meanwhile, if you have questions, feel free to just jump up. So all these demos, all these manifests are in the Kepler's repo. You can choose that for your workload validation. The first, sorry, I just got messed up. The first workload we demo is the GPU workloads. So now you see, sorry, actually we created both GPU and CPU workloads. And the first thing we are going to see is the CPU, the part, the CPU part, the CPU workload path. Okay. So on the top left, that's the way we choose the namespace and the path. So we just pin to the rice namespace, and we can find the rice. Okay, so this is a random CPU, random generator CPU path. You see all of a sudden this there's a spike on CPU's utilization, and then the aggregates carbon footprints by different the fuel energy is also gets updated. I'm going to just pause here and quickly go to the next slide. So this power reporting is the capability of Kepler, and you can integrate yet another layers of information to get the sense of your energy consumption by workloads as a data center level and at the carbon level. Because from the power, there's still some translation into carbon. You used to need a different information. For example, the carbon intensity from your power grid. And you also need information from the data center PUE, using that information to build up the comprehensive carbon dashboard. We have some demos around that area. So if you can scan the CL code, you can find out our repo over there. And very lastly, since this is the end of the day, your feedbacks about this conference is welcome. It's really appreciated. If you can scan it, and make our programs more sustainable, that is all good for the future. Now I'm ready for questions and directions. And we can do some fun exercise of tossing the microphone. Right. After that, it's going to be happy hour to boost up our energy. It's going to be the equivalence. If you can repeat your question, that'd be great. So let me see if I can rephrase your question in my understanding. So where else do I see the energy efficiency my way?
Yeah.
I think that's great. I think a lot of energy savings we can use nowadays by configuring our workload resource configuration in the right way. You know, if you're over provision and overspending your resource, obviously that's will come up with suboptimal energy savings. So our goal is to pinpoint exactly how much energy used and how much energy can be saved. So that's come from two ways. The one is that we have to have a deeper understanding of the workloads we are using. The second is about the operation of your organization, right? If you know that you are going to have follow the sun schedule, you shut down your idling, or you just tune down your workloads or your configuration as nice. That's going to save you lots of energy. If you don't know what's the pattern of your operation, then you can use our automated tools in the future. That's going to help you. I feel that it's almost come to the point of we have to have a lot of conversations with end users, with operators, and with the people who are writing the programs to have deep understanding how we can tune their workloads, how we can understand what they really require, so that we can save their energy. It's just like the Nest. Do you have Nest at home or any kind of equivalent? I just wave hands. That's the kind of thing we want to use. If you understand your work schedules, understand your home temperature requirements, we can make the Nest go as efficient as we can. Right? Yes, go ahead.
So do you envision this making changes across a network all day, every day? So, like let's say I have a broad data center network and some of the edge devices and some core devices, and I have a different paradigm for the time that these are using a lot of power as opposed to those are using a lot of power. Am I kind of visualizing that and then making real-time decisions to make changes to like all day long, every day?
Well, we don't want to overburden your work already. I do not want you to watch for outage and at the same time watch for the energy consumption.
Yeah.
That's not the goal. The goal here is that make your life easier, right? We do not want to, you have the sustainability objective. We want to make your life easier. So we want to optimize this process by providing these tools for you. One is the scheduling, the other one is VPA, the vertical path autoscaling. So by tuning down up and down the frequency and tuning up and down the resource consumption, we can make your objective met by this tool. So that's the way we want to make our life easier and still have our goals met. If you are just watching your real time of 24/7, how much energy is consumed by each user, that's going to defeat our sustainable goal. So your life is going to be unsustainable. And that also creates a lot of manual interventions, which may not be the best way for any of our jobs. I think you have lots of energy, but
we sure do.
Let's save your energy for better missions.
Thank you.
Yeah, you're welcome.
Thank you.
All right. I see we are coming close to the end, and thank you for your participation. And again, scan the QR code, make our program sustainable, and join our contributions. And either by creating a PR, creating an issue, or just shoot us an email contacting any of the Red Hat solution architects. That'd be great.
Yeah, can you put the survey code up a little bit longer?
Okay, yeah, oh, sure. Thank you.